Hello everyone and welcome back to PC Retro Programmer. In the past few videos in this advanced CGA Graphics series, we've been trying to figure out how to do cycle accurate graphics effects. And I actually have an effect in mind that I want to show on the channel. But before we can do that, there's a couple of other things that we need to sort out. So far, we have things so that the machine is completely silent. Obviously, if anything happens to interrupt the CPU while it's running our frame loop, then it's going to mess up any cycle accurate timing we're doing. So what we've done is we've turned off all of the interrupts except for two. One of them is a timer interrupt, which we set up to run at exactly the same point every frame. And this actually wakes the CPU up at the start of our frame loop. And the other one is the keyboard interrupts. We've left those enabled because we want to be able to exit to DOS when a key is pressed, when the program is finished. But other than that, everything else is switched off. We even turned off dynamic RAM refresh, which also interferes with the CPU, or at least with the bus, and this has made the machine completely silent. But there are a couple of other things that we need to be able to do. First of all, every time we start the program at the moment, things end up being in a slightly different place, and that's because we've not synchronized the CPU with the graphics system. This is called lockstep, and it'll be a topic for a later video. The other thing that we need to deal with is the one we're going to look at today, and that is keyboard input. Now, obviously, what we said is true. If you just want to press a key to go to DOS, it doesn't really matter when this happens. The program is over at that point and you don't need cycle accurate timing anymore. But it turns out that while we're developing this program, we're going to need to be able to adjust the timing very precisely down to the cycle. And the easiest way to do that while developing the program is to press keys on the keyboard to change the size of various loops and to increase and decrease the number of cycles at various points in the program. And so it's useful to be able to press keys to do this. Now, it won't work to use interrupts for that. If a key is pressed at a really critical point, it will mess up our cycle accurate timing and it just won't recover. So we need to be able to access the keyboard without using interrupts, and so that's the topic of today's video. Now, the first thing that we need to deal with the keyboard is to figure out when a key has been pressed. The way this normally happens is the keyboard controller sends a request along an interrupt request line to the CPU to demand attention. There are 8 of these in the PC, numbered 0 through 7. For example, 0 is for the timer, interrupt request line 1 is for the keyboard, and so on. And we don't want the keyboard to be able to interrupt the CPU, and fortunately for us, the interrupt request lines are not wired directly to the CPU, but go through another chip called the PIC, which allows us to control them. So the PIC serves a number of different functions. One of the functions is just to arbitrate between all the different requests. If multiple devices request attention at the same time, the CPU wouldn't know which one to handle. And so it prioritizes them and just sends them one at a time to the CPU. But a second function that the PIC provides is it allows us to mask off the individual request lines. So the first thing we're going to do today is we're going to set bit 1 of the interrupt mask register, and this will mask off interrupt request line 1, the one for the keyboard, and prevent any requests getting through to the CPU and messing up our timing. Now, the other thing that the PIC does is it keeps a record of which interrupt request lines are active at any given time. There's another register in the PIC called the interrupt request register, and each bit of that corresponds to one of the request lines, and when they're active, when some device is requesting attention along that line, the corresponding bit gets set. So what we can do is we can read the interrupt request register to see if bit 1 is set, which would mean that the keyboard's requesting attention. It won't get any because the request is not going to be forwarded to the CPU because we'll have masked that off, but the request is still recorded in that register. Now, unfortunately, there's a lot of incorrect information about the PIC online, and most websites just say that you can't access the interrupt request register that's just internal. This is not true. According to the datasheet from Intel, you can read it. It's just a little bit complicated. You have to use control words to do this. And so in today's video, I'm going to go through, first of all, how to use the interrupt mask register, and then secondly, how to send these control words to deal with the interrupt request register. Okay, first of all, let's deal with the interrupt mask register, which is the easiest of the PIC registers to deal with on the PC. You can see on the left-hand side here, there are two ports for accessing the programmable interrupt controller, the PIC. There's port 20 hexadecimal and port 21 hexadecimal. Now, I'll start by giving a simplified description of how to deal with these, and that will be enough to allow us to deal with the interrupt mask register. So first of all, you can think of port 20 as some kind of command status register. If you write to it, you're sending a command to the PIC, and if you read from it, you're reading some kind of status. Port 21, on the other hand, is just directly wired up to the interrupt mask register of the PIC, and that's why it makes it particularly easy to deal with this register. It's even set out in a very logical way. Bits 0 to 7 of this register correspond to interrupt request lines 0 through 7. So what we want to do is we want to mask off interrupt request line 1, and what that means is to set bit 1 of this register. And it's done in the easiest way you can imagine. Basically, you just read in the current value from port 21 hexadecimal, and you modify the appropriate bit. In our case, it'll be bit 1, which corresponds to the keyboard request line, and then you write the value back out to the port. So it couldn't be easier. But I said that was a simplified description. Now I need to go through a slightly more detailed description, which will allow us to figure out how to deal with the interrupt request register, which is much more complicated. First of all, the PIC is a chip in the PC that's controlled using what are known as control words. So there are actually two different kinds of control words that the PIC accepts. There are initialization control words and operation control words. Unfortunately for us, we don't need to deal with the initialization control words. That's a good thing because they're quite complex, and these are all sent in a specific order by the BIOS when the machine boots up to initialize the PIC. So there are three different operation control words, and it turns out that operation control word 1 is sent for changing the value of the interrupt mask register. And as I said, this was done in a very simple way on the PC. Basically, when you write to port 21 hexadecimal, you're automatically sending an operation control word 1 and therefore writing to the interrupt mask register. But unfortunately, the control words 2 and 3 are a little bit more complicated. As you can see, they're both covered here by port 20 of the PIC. And so the first thing that we have to do is to be able to distinguish between which control word we're sending. And that's done with bits 3 and 4 of the value that you send to port 20. So if you set these to 00, then you're sending a control word 2 to the PIC. And if you set these to 01, then you're sending a control word 3. And then the remaining bits of the byte that you're writing to this port then get interpreted differently depending whether it's a control word 2 or a control word 3. So I've written out the description of what the bits mean if you're sending a control word 2, and then below that I've written out what the bits mean if you're sending a control word 3. So let's start first of all with a control word 2. We won't actually need that in today's video, but we might as well cover it while we're here. So operation control word 2 can be used to send a bunch of different commands to the PIC, and I won't list them all, they're in the datasheet after all if you're interested. I just want to highlight a couple which are used more often, the end of interrupt commands. So if you're writing a software interrupt handler to deal with one of these hardware interrupts that comes in on one of these lines and gets forwarded to the CPU to be dealt with, then once that handler is finished, it needs to notify the PIC so that the PIC can reset the line so it can be used again. And this is done using an end of interrupt command. Now, under normal circumstances, the PIC actually knows which interrupt request line it asks the CPU to handle, and so all the handler would have to do is say to the PIC, hey, I'm done. And this is done using a non-specific end of interrupt command. So command 001, you just put that value in bits 5 to 7 of operation control word 2, and that's all the handler needs to do. But in some other situations, it might actually be necessary to tell the PIC specifically which interrupt request line you finished handling. Maybe you were handling multiple of them at the same time, you did them out of order, or maybe the PIC is in some bizarre mode that requires some additional work, and so then it's necessary to notify which interrupt request line you dealt with. And that's done with a specific end of interrupt command, or command 011, and along with that you have to specify which one you dealt with. You put the value into bits 0 to 2 of the operation control word 2. It's just 3 bits because it's just a value from 0 to 7 after all. So I won't cover any of the other commands. As I said, let's move on to operation control word 3. This one allows us to get access to 2 registers, the interrupt request register that we're interested in, and another one called the in-service register. Now, the in-service register keeps a record of which interrupt request lines the PIC has asked the CPU to handle. There could be multiple ones, of course, because interrupts can actually interrupt other interrupts if they have high enough precedence. And so this register would keep a record of which ones the CPU had been asked to handle, the ones that are in service by the CPU. We won't need that today. Instead, we're going to put the value 10 in the first couple of bits of our operation control word 3, and that will tell it we want to read the interrupt request register. Once we output that to port 20, when we read this port again, that will then contain the value of the interrupt request register. So that's how we're going to get access to it today. Now, there's a couple of other things you can do with operation control word 3. There's a poll mode. So basically what this does is allow the CPU to actually request a interrupt line to handle at a time of its choosing. So it could just poll the PIC instead of waiting for the PIC to interrupt it. And we won't actually be doing that in today's video. It's enough for us to just look at that interrupt request register and see if the keyboard's raised a request. So we don't need to do a poll. Now, the other thing you can do is something called a special mask mode. I won't go into the details of why you'd want to do this, but basically what it does is it masks off the interrupt request line that you're currently handling and leaves all the other ones open. And there are various special modes of the PIC where this is actually necessary. But anyway, we now have enough information to access these 2 registers that we need. Let's move on to the code and see how all of this is done in practice. Now, I've put the code for today's episode in keypress.asm, which you can find at the link in the description. And it turns out that we already had code in our program before for masking off all the other interrupts. And so basically, all we're going to need to do to mask off the keyboard is just to set 1 additional bit in the interrupt mask register. So you can see we access that by reading port 21. We set all the bits that we want, and then we write back out to port 2.1. And the only thing that I've changed here is this value. It was set to OFC before, and now it's set to OFE, which just masks off that one extra bit. And so that's all that's required. Now the keyboard won't interrupt the CPU. So let's move down to our frame loop, and let's take a look at what I've changed there. So here's the new code that I've inserted. And basically what this is going to do is write out to that port 020, and it has to first of all select the operation control word 3, and it also has to select the read interrupt request register bits, and so that all works out to OA in hexadecimal if you work out what the binary bits code in hexadecimal. So we write that out to port 20, and then once we read in from that port again, we'll have the value of the interrupt request register. And of course, we're only interested to know if the interrupt request line 1 is currently active. In other words, if the keyboard is requesting attention, and for this we just need to test that bit 1, which is the same as testing the value 2 in hexadecimal. And there are two options. Either there was 0 after we did this test, that means the bit was not set, the keyboard's not asking for anything, and so we jump down to here, no key. We can do whatever else we want for the rest of our frame loop, and then finally jump to the beginning of our frame loop again. The other option is that this falls through. That's because a key was pressed, and that'll jump us down to here where we can actually handle the key press. And for this, we're going to access the keyboard directly, and there are actually ports that allow us to do that. So now I actually need to describe how the keyboard ports work. Now I know you'd like accurate information for the keyboard, but there were some differences between the PC and XT and AT keyboards, and unfortunately most resources give information for the latter and just assume it was the same. In fact, the very thick book that I have on early PC hardware just summarizes for the PC and XT keyboard and then warns that all the detailed information they have is only accurate for AT and above. So I'm going to have to do the same. I'll give information which will work for the PC and XT keyboard, but I'm not 100% sure it's accurate in detail. In particular, I've read that the protocol for the PC and XT keyboard was just slightly different, but the routine that I'm going to show will still work on those keyboards. Now, the two registers we're going to need to deal with are at ports 60 and 61. We've got a keyboard buffer, which will tell us what key was pressed, and a status and control port, depending if you're reading or writing it, at port 61. And I'll talk about that in a moment. Now, buffer might be a little bit of a generous term. I don't actually know how big the buffers were in the early keyboards. I've read 16 keys, but unfortunately this is suspiciously the exact size of the BIOS keyboard buffer, which is not the same thing, so I don't know if that information is really relevant. At any rate, this is where we'll look to see what key was pressed, and actually we'll get an interrupt request notification when a key is either pressed or released. And so we don't want to deal with every key twice. We're going to have to ignore one of these. And the way you tell the difference is that the value in the keyboard buffer, called a Scancode, has two different kinds. When a key is pressed, you get a make code, and when it's released, you get a break code. And basically the difference is that the break code has the top bit set. So we'll read this, and then once we've done that, we need to go through this little routine called a handshake routine to let the keyboard know that we've successfully read a value from the keyboard buffer and that it can move on. So this is best explained just by looking at the code itself. So at this point in the code, we've already had an interrupt request notification telling us the keyboard wants attention. So we know there's a key press or a key release. And so at this point, what we're going to do is read the keyboard buffer to get that scan code. And we'll just save it in the DL register for now, and we'll look at that a little bit later. Our first order of business is to go through this handshake routine. It's a strange little dance that we have to go through to let the keyboard know that we've dealt with a key. So there are 3 steps. The first one is to read the system control port at port 61, and we'll put the value aside for now because we're going to need it again in just a moment. And we take a copy of that and set the top bit, and then write that value back out to the system control port to acknowledge to the keyboard that we got this value. And then the final step is to take the original value that we read just a moment ago and write that out to the same port. And that finishes off our handshaking routine. So it's a little bit strange, but this is what the keyboard will recognize. So now we're free and clear, we can take a look at our scan code and see what key was pressed. And I made the arbitrary choice to just ignore key releases. I only want to know when the key is pressed. So for that I need to look at the top bit to see if it's a break code. I do this by shifting the value left by 1 bit, and that will shift the top bit into the carry flag. And then I can use a conditional jump instruction based on the carry flag. So if it was a key release, I just want to ignore those. So I won't do anything, I'll just jump back to the beginning of my frame loop. And if it was a key press, I'll be at this point here. And what I'm going to do is shift the scan code back to the right again, so that it's an unshifted scan code. And then I'm going to take a look at it and see what key it corresponded to. Now here you have to be a little bit careful. A scan code is not an ASCII code. They're different, and also scan codes vary depending on what kind of keyboard you have. Well, technically the scan codes are the same, but if you have, for example, a German or French keyboard, all the keys will be messed up, and so the values will be different. So you really need a table that corresponds to your keyboard. Now I know that for a British and American keyboard, Scancode 16 corresponds to the Q key. Unfortunately, many of the Scancode tables online are just incorrect, so you might have to look around for one that's right. But at any rate, here I check for Q, and if that was the key that was pressed, I just want to exit to DOS. So I'll jump down to my exit routine, which was already there before, it just exits to DOS. And if the Q key was not pressed, then I could actually go on and check other keys here if I wanted to, but I'm not going to do that. I'm actually going to ignore all the other keys and just jump to the beginning of my frame loop. Now it's actually up to you what you do with the information that you get from the keyboard. So there's not a separate scan code for lower and uppercase A, for example. So you actually need to keep track of whether or not the shift key was being held down when the A key was tapped in order to know whether it's lower or uppercase. And so there's a little bit of work involved in dealing with the keyboard, but for what we're doing, it's pretty straightforward. At any rate, this is all we need to do here. Let's run this code and see what the result is. Well, this is our program, and if we run it, you can see that it's rock solid. There's no jitter whatsoever. And in fact, if I press a bunch of random keys, it doesn't interrupt it at all, which is exactly what we want to see. And if I press the Q key, it exits to DOS. So the program is working. I've only tested it so far with Marty PC, but if you don't hear it differently, then I'm sure it worked also on genuine hardware. Now, what I used to do a little bit differently in the past is after the handshake routine, I used to do an end of interrupt command with the pick. And my reasoning was that what we're doing here is kind of similar to an interrupt handler for the keyboard, so maybe I should acknowledge the end of that with the pick. But I actually think that this is only necessary if the interrupt request was in service with the CPU. And it's really only required to reset the in-service register, not the interrupt request register. And in our case, the interrupt request is never in service with the CPU because we never let it reach the CPU. We just deal with it ourselves. And what I think happens here is that as soon as the keyboard is satisfied that it's been dealt with, it lowers the interrupt request, and that reflects immediately in the interrupt request register. I will test it after I finish this video on genuine hardware just to make sure. So it looks like we finally are able to control the keyboard without messing up our cycle accurate timing, and so now we're ready to move on to the next step in trying to get a cycle accurate graphics effect.